If we know the channel impulse response and its statistics, then we can calculate the error probability for a given threshold. In recent videos, we've been laying the groundwork to talk about diffusion-based molecular communication. I introduced molecule diffusion, I discussed how we characterize the diffusion signal between the transmitter and receiver, I presented an algorithm for simulating diffusion, and I summarized diffusion counting statistics. We now have all the necessary pieces to introduce a simple communication system based on diffusion. In this video, I'm going to take what we've learned about diffusion and map it to the fundamental components of a communication system. The 5 fundamental components of a communication system are the source, transmitter, environment, receiver, and destination. The source has a message that it wants to send to the destination. Let's have the source create a simple message, just one binary symbol, which can be a 0 or a 1. The transmitter needs to modulate this binary symbol. This means that it has to create a different transmission depending on the value of the symbol. Let's stick with on-off keying, so the transmitter will release a payload of molecules for binary 1 and release nothing for binary 0. The transmitter and receiver are placed in an ideal diffusion environment with no obstacles and no chemical reactions. This means that the released molecules for binary 1 will randomly spread away from the transmitter according to fixed laws of diffusion. Some of these molecules will enter into the space that is watched by the receiver. The receiver has instructions on when to count the molecules. Let's say that the receiver will only count the molecules once. The best time to count will be when we expect the signal from the transmitter to be strongest, and we know this time from the channel impulse response. The receiver will take the measurement and then need to decide whether molecules were released by the transmitter. A simple solution is to use a threshold. So if the receiver counts the threshold number of molecules or more, then it should decide that the symbol is a 1. Since we only have one symbol, and we assume that there are no extra molecules in the environment, then the threshold should be 1. So if the receiver counts any molecules, then it should conclude that the transmitter released them, and that the transmitted symbol is a 1. If no molecules are counted, then the receiver should conclude that nothing was released, and that the transmitted symbol is a 0. We already see that it's possible for the receiver to make a mistake. If the transmitter releases molecules, but none are observed when the receiver is counting, then it will decide a 0 when the actual symbol is a 1. This is referred to as a receiver error. The chance of making an error, called the error probability, is an important communication metric. Another way to make an error is to decide a 1 when the actual symbol is a 0. This shouldn't happen when we only send one binary symbol and have no extra molecules in the environment. However, if we want to send more than one symbol, then we need to repeat this whole process. This means that there can be molecules from a previous transmission that are still diffusing near the receiver when we want to send another symbol. So there's a chance that we might count an old molecule by mistake. We can trade off between the two types of error by adjusting our decision threshold. If we know the channel impulse response and its statistics, then we can calculate the error probability for a given threshold. If the performance is poor, then we can consider a more advanced receiver design. We'll go over error probability analysis and other receiver designs in future videos. Thanks for watching. Did you learn something? You can let me know in the comments. You can also like the video and subscribe if you'd like to see more research highlights and tutorials on biophysical communication engineering. See you next time.